Welcome to this problem walkthrough. Today, we'll be exploring problem number 751, titled IP to CIDR. In this problem, we aim to take a range of IP addresses and represent them efficiently using CIDR, classless interdomain routing, blocks. Get ready to dive into the details and learn some interesting techniques to solve this problem. The problem requires us to generate a list of CIDR blocks that cover a specified range of IP addresses. A CIDR block is a compact way to represent a contiguous range of IP addresses using an IP address and a prefix length. For example, the CIDR block 192.168.1.0/24 represents all IPs from 192.168.1.0 to 192.168.1.255, a total of 256 addresses. Given a starting IP address and a number n, which specifies the count of IPs to include in the range, we need to determine the smallest number of CIDR blocks that fully cover the range from the starting IP up to the nth address. The input will include the starting IP as a string and the count n as an integer, and the output will be a list of CIDR blocks that meet these requirements. Let's consider an example to clarify the task. If the starting IP is 255.0.0.7 and n is 10, the range to cover is the 10 addresses starting from 255.0.0.7, which means 255.0.0.7, 255.0.0.16. The first CIDR block, 255.0.0.7/32, covers only the first IP, 255.0.0.7. The second block, 255.0.0.8/31, covers two IPs, 255.0.0.8 and 255.0.0.9. Similarly, 255.0.0.10/31 covers the next two IPs, 255.0.0.10 and 255.0.0.11. This process continues until all 10 IPs are covered using the smallest possible number of CIDR blocks. Now, in a different example, if the starting IP is 192.168.0.0 and n is 4, the range to cover is 192.168.0.0, 192.168.0.4. In this case, the entire range of 4 addresses, from 192.168.0.0 to 192.168.0.3, can be represented by a single CIDR block, 192.168.0.0/30. This demonstrates how the prefix length of the CIDR block allows us to efficiently represent a group of addresses, minimizing the number of blocks required. For a third example, consider the starting IP 0.0.0.0 with n equal to 1. Here, the range is simply 0.0.0.0, 0.0.0.1, meaning only one IP address needs to be covered. The CIDR block in this case is 0.0.0.0/32, which represents exactly one address. This is the most specific CIDR block possible, as the prefix length of 32 means no additional IPs are included in the range. This example highlights how CIDR blocks handle single address cases efficiently. When solving this problem, there are some important constraints and edge cases to consider. First, the starting IP will always be a valid IPv4 address, and n will range from 1 to 10,000. The output list must contain no more than n CIDR blocks. When generating CIDR blocks for large ranges, it's essential to use the largest possible subnet masks to minimize the number of blocks. Additionally, care must be taken to ensure that the generated CIDR blocks do not cross IPv4 boundaries, such as wrapping from 255.255.255.255 to 0.0.0.0. By carefully managing these constraints, we can create an efficient and accurate solution for the problem. To approach the problem of converting a range of IP addresses into CIDR blocks, let's first consider a brute force method. This involves iterating over the range of n IP addresses, starting from the given start IP, and assigning each IP address to its own /32 CIDR block. Since each /32 block represents precisely one IP address, this ensures that all addresses are covered. However, this method is inefficient because if n is large, the number of CIDR blocks will also match n, resulting in a massive, impractical output. Moreover, this method does not take advantage of the opportunity to combine consecutive IP addresses into larger, more compact CIDR blocks. Instead, we can use an optimized approach that leverages the properties of CIDR notation. The key insight here is to use power of 2 alignment, where CIDR blocks represent ranges of IP addresses in sizes that are powers of 2, for example, address/3241 address/3142/344, and so on. By aligning the CIDR blocks with the start IP and iteratively merging as many IP addresses as possible into the largest blocks, we can significantly reduce the total number of CIDR blocks needed for the range. The optimized approach focuses on using bitwise operations to calculate the largest possible CIDR block that aligns with the start IP address and fits within the remaining range of n. This ensures that we cover the maximum number of IPs in each step while maintaining alignment. Once a block is determined, the start IP and the remaining n are updated, and the process continues until all IPs in the range are covered when n becomes 0. This strategy is efficient because it avoids the need to process each IP individually. Instead, it uses the binary representation of the IP address to find the largest possible block size that maintains alignment and fits within the range. The steps are straightforward. First, convert the start IP into its 32-bit integer form to simplify calculations. Then, in a loop, compute the largest aligned block size, append the corresponding CIDR notation to the result, and update the start IP and n accordingly. Finally, convert the numerical results back into CIDR format. This method is both time-efficient and space-efficient, as it minimizes redundant computations and produces a concise list of CIDR blocks. When comparing the brute force approach to the optimized method, the differences are significant. In terms of time complexity, the brute force approach requires O(n) operations, as it processes each IP address individually. On the other hand, the optimized approach reduces this to O log n, by iteratively having the range of n with each step. This makes the optimized approach far more scalable for large values of n. Additionally, the result size is another area where the optimized method shines. By merging consecutive IPs into larger CIDR blocks, it generates significantly fewer blocks compared to the brute force method, which produces one block per IP. While the brute force approach is simpler to implement and easy to understand, it sacrifices efficiency. The optimized approach, though slightly more complex, offers a much better balance between clarity and performance. This is why the optimized solution is preferred. It is scalable, reduces computational overhead, and ensures that the number of CIDR blocks remains minimal. Overall, it provides the most practical and efficient way to solve the problem, especially for larger ranges of IP addresses. The algorithm begins by understanding the problem of converting a range of IP addresses into the most compact representation using CIDR blocks. A CIDR block is defined by a base IP address followed by a prefix length that determines how many addresses are included in the block. A smaller prefix length covers a larger range of addresses. To tackle this, we start with the given IP address and the count of addresses n. The challenge is to repeatedly identify the largest possible block of addresses, expressed as a power of 2, within the remaining range. Once identified, the block is output as a CIDR notation, and the process continues until all n addresses are accounted for. The first step is to convert the starting IP address into a 32-bit integer. This conversion makes it easier to work with the IP mathematically, especially when calculating blocks and aligning them to powers of 2. For example, the IP 192.168.1.0 is converted to its binary representation, which simplifies further calculations. Next, we process the range of n IPs to generate the CIDR blocks. We initialize a list to store the resulting CIDR notations. While there are still addresses remaining to process, the algorithm determines the largest block, expressed as a power of 2, that can fit within the current starting IP and does not exceed n. The size of this block depends on the number of trailing zeros in the binary representation of the starting IP. For instance, if the starting IP is 192.168.1.0 and n is 10, the largest block fitting the range is 8 addresses, represented as 192.168.1.0/29. Once the block size is determined, the prefix length is calculated as 32 minus the log base 2 of the block size. This prefix length ensures the CIDR block is accurately defined. The block is added to the result list, and the remaining count of addresses is reduced by the block size. The starting IP is also incremented by the block size, ensuring the algorithm moves to the next unprocessed range. After processing all the IPs, the next step is to convert the results back into standard CIDR notation. Each 32-bit integer representation of the IP address is converted into its dotted decimal format, such as 192.168.1.0, and paired with its corresponding prefix length to form the CIDR block. These blocks are then returned as the final output. The key insight here is the efficiency of CIDR representation. By grouping IPs into the fewest possible blocks, memory usage is minimized, and routing tables are simplified. The alignment to powers of 2 ensures that blocks are non-overlapping and maximally compressed. Additionally, the iterative approach of reducing n and adjusting the starting IP ensures that each address in the range is covered without duplication or omission. This systematic process makes the algorithm both efficient and robust. To implement the algorithm effectively, specific data structures and operations are utilized. First, converting IP addresses into 32-bit integers allows for straightforward arithmetic operations, such as addition and alignment. For example, the IP 192.168.1.0 becomes 32322357776, enabling calculations like determining the largest power of 2 that fits the range. The resulting CIDR blocks are stored in a list as strings, such as 192.168.1.0/29. Key operations include parsing IPs into integers, calculating powers of 2 to find the largest block, and determining the correct prefix length for CIDR notation. By dynamically adjusting the starting IP and reducing n by the block size in each iteration, the algorithm ensures that no addresses are missed and that the range is processed efficiently. These steps are critical for maintaining both the correctness and performance of the solution. Finally, let's analyze the algorithm's complexity. The time complexity is O log n, as each iteration reduces the count of remaining addresses n by a power of 2. This logarithmic reduction ensures the algorithm processes large ranges efficiently. The space complexity is O(1), excluding the output list, since the algorithm uses a constant amount of extra space for calculations and intermediate variables. This makes the solution not only fast but also memory efficient. Together, the logarithmic time complexity and minimal space usage demonstrate the scalability and practicality of the algorithm, even for very large ranges of IP addresses. Here, we define a solution class with the method IP to CIDR, which takes an IP address and a number n as inputs. The first helper function, IP_to_int, converts a dotted decimal IP address into its integer equivalent using bitwise operations. Each segment of the IP is extracted, shifted to its proper position, and combined into a single integer value. Similarly, the int_to_IP function does the reverse. It takes an integer and reconstructs the dotted decimal format by extracting each byte using bitwise shifts and masks. In the main method, we start by converting the given IP address to its integer form using IP_to_int. We then initialize an empty list called result to store the CIDR blocks. Inside the loop, the goal is to calculate the largest possible block size that aligns with the current starting address and fits within the remaining count of n. To achieve this, we calculate max_mask, which determines the prefix length of the CIDR block. By checking if the starting address is divisible by powers of 2, we find the largest block that aligns with the address. Then, we ensure that this block size doesn't exceed n by incrementally adjusting the mask. Once the block is valid, we append it to the results list in CIDR format, update the starting address, and subtract the block size from n. Finally, the method returns the result list, which contains all the CIDR blocks that represent the range of IP addresses. This approach ensures that the IP range is split into the fewest possible number of CIDR blocks while adhering to alignment constraints. By iteratively calculating the largest blocks that fit, the algorithm efficiently handles the conversion and produces an optimized output. Here, we begin by defining a Java class named solution and implementing 2 utility methods that will help with the conversion between IP address formats. The first method, IP_to_, takes an IP address as a string and converts it into its integer representation. It does this by splitting the string into its 4 parts using the dot as a delimiter, parsing each part as a long, and then combining them using bit shifting. This allows us to represent the IP address as a single 32-bit integer for easier manipulation. The second method, long_to_IP, performs the reverse operation. Given an integer representation of an IP address, it reconstructs the string format by extracting each byte using bitwise operations and formatting it back into a dot-separated string. These conversions are essential for efficiently working with IP ranges. Finally, the IP to CIDR method is introduced, which will calculate the CIDR blocks. It begins by converting the starting IP into its integer form using iptalone, initializing a list to store results, and setting up a loop to process n blocks. Now within the loop, we calculate the largest possible CIDR block that can fit within the current range. We start by setting maxmask to 32, which represents the smallest possible block size, and then reduce it step by step. The goal is to find the largest mask where the starting address is aligned to the block size defined by the mask. This alignment check is done by ensuring that start modulo the block size equals 0. Once we find such a mask, we ensure that the block size does not exceed the remaining count of IPs n. If it does, we increment the mask and reduce the block size accordingly. With the correct mask determined, we construct the CIDR notation string by converting the current start address back to its string format using long2IP, appending the mask, and adding the result to our list. We then update the start address by advancing it by the block size and decrement n by the same amount. This process repeats until all required blocks are generated, and finally, the resulting list of CIDR blocks is returned. To solve the problem of converting an IP address and a given number of addresses into CIDR blocks, we start with the example of IP 192.168.1.0 and n equals 4. Using the formula 192.24 plus 168.16 plus 18 plus 0, the integer is calculated as 323.223.5776. Next, we initialize three variables. Start is set to the integer representation of the IP, which is 323.223.5776, n is set to 4, as given in the problem, and result is initialized as an empty list to store the CIDR blocks. In this case, 323.223.5776 is divisible by 2 32 to 32, so we keep max_mask as 32. We then append the first CIDR block, 192.168.1.0/32, to the result list, update start to 323.223.5777, and reduce n by 1, making it 3. First, we convert the IP into its integer representation. The IP is split into its four parts, 192, 168, 1, and 0. Now, we need to determine the maximum mask size. Starting with max_mask equals 32, we check if the integer can be divided evenly by 2 32 max_mask. Next, we calculate the maximum block size using the formula 1, 32 max_mask, which gives us 1. Since this block size is less than or equal to n, we proceed without changing the mask size. Now, we repeat this process for the remaining values of n. For start equals 323.223.5777 and n equals 3, the maximum mask size remains 32, and we append the CIDR block 192.168.1.1/32 to the result list. We then increment start to 323.223.5778 and reduce n to 2. Similarly, for start equals 323.223.5778 and n equals 2, the maximum mask size is still 32, and we append 192.168.1.2/32 to the result list. After this, start is updated to 323.223.5779, and n becomes 1. Finally, for start equals 323.223.5779 and n equals 1, the maximum mask size again remains 32, and we add 192.168.1.3/32 to the result list. At this point, n becomes 0, so we stop the process. The final output for this example is the list of CIDR blocks, 192.168.1.0/32, 192.168.1.1/32, 192.168.1.2/32, 192.168.1.3/32. In the second example, we are asked to convert the IP 10.0.0.0 with n equals 8 into CIDR blocks. We begin by converting the IP to its integer representation. Using the same formula as before, 10.0.0.0.0 is converted to the integer 167772160. We then initialize the variables. Start is set to 167772160, n is set to 8, and result is initialized as an empty list. Next, we determine the maximum mask size. For start equals 167772160, we find that max_mask equals 29 satisfies the condition start %, 1, 32 max_mask == 0. The block size, calculated as 1, 32 max_mask, is 8, which matches the given n. We then append the CIDR block 10.0.0.0/29 to the result list. Since the entire block size equals n, we update start to 1677721168 and reduce n to 0, ending the process. The final output for this example is the list 10.0.0.0/29. In the third example, we are tasked with converting the IP 255.255.255.0 and n equals 2 into CIDR blocks. First, we convert the IP to its integer representation, which results in 429.496.7040. We initialize the variables as follows: start is set to 429.496.7040, n is set to 2, and result is initialized as an empty list. To find the maximum mask size, we check the condition start %1, 32 max_mask == 0 for various values of max_mask. Here, max_mask equals 31 satisfies the condition. The block size, calculated as 1, 32 max_mask, is 2, which matches the given n. We then append the CIDR block 255.255.255.0/31 to the result list, update start to 429.496.7042, and reduce n to 0, completing the process. The final output for this example is the list 255.255.255.0/31. The IP to CIDR function begins with operations to convert between IP addresses and their integer representations. The IP_to_int function takes an IPv4 address, splits it into its 4 components, and uses bitwise operations to compute a single integer. This process involves a fixed number of steps, splitting the address into 4 parts and performing 4 integer conversions with bitwise shifts. Since these steps are constant regardless of the input, the time complexity is O(1). Similarly, the reverse process, carried out by the int_to_IP function, formats the integer back into the dotted decimal format using bitwise operations in string processing. This reversal also completes in constant time, making its time complexity O(1). Together, these conversion operations do not depend on the size of the input n and are therefore constant in complexity. The main loop of the function operates while n is greater than 0. During each iteration, the algorithm calculates the largest power of 2-aligned block size that fits within the current start IP and does not exceed the remaining n. To achieve this, the first inner loop determines max_mask, which involves at most 32 iterations for a 32-bit IP address, making it O(1). Next, the second inner loop adjusts the block size to ensure it fits within n, which also requires at most 32 iterations and is O(1). Once these calculations are complete, the CIDR block is appended to the result list, and the start and end values are updated. These updates are constant time operations. The number of iterations of the main loop depends on the number of CIDR blocks generated, which is proportional to O log n, since each block reduces n by at least 1 and usually by a larger power of 2. Combining these factors, the overall time complexity of the function is O log n, as the loop performs constant work in each iteration and runs logarithmically with respect to n. The space complexity of the algorithm is determined by 2 main factors. First, the auxiliary space used for variables like start, max_mask, and max_block_size is constant because these are simple integers, resulting in an O(1) space usage. Second, the result list, which stores the generated CIDR blocks, contributes to the overall space complexity. In the worst case, the number of CIDR blocks is proportional to O log n, as the algorithm minimizes the number of blocks by covering ranges of IPs using powers of 2. Each CIDR block is represented as a fixed-length string in IPv4 format, so the space required for each block is O(1). Therefore, the total space used by the result list grows logarithmically with n. Combining these factors, the overall space complexity of the algorithm is O log n, dominated by the storage requirements of the result list. To better understand the efficiency of the current solution, let's compare it to a brute force approach. A naive method might generate each of the n IPs individually and then convert them into CIDR blocks. This approach would result in a time complexity of O(n), as it involves processing each IP, and a space complexity of O(n) to store all the generated IPs. In contrast, the optimized algorithm avoids explicitly generating every IP and directly calculates the minimal set of CIDR blocks. This drastically reduces both time and space complexity to O log n. The logarithmic efficiency is achieved by leveraging power of 2 alignment, which minimizes the number of CIDR blocks. Each block represents a range of IPs, allowing the algorithm to exponentially decrease the remaining n in each iteration. This power of 2 strategy is the key to the algorithm's significant optimization. The algorithm's efficiency holds across best, average, and worst-case scenarios. In the best case, where n equals 1, only one iteration is needed to process the single IP, resulting in a time complexity of O(1). For a general input size n, the time complexity averages to O log n, because the algorithm reduces n exponentially in each step. The worst case, 2, adheres to O log n, as the algorithm consistently reduces n by powers of 2, regardless of the input distribution. The mathematical basis for this complexity lies in the nature of binary representation. Each iteration effectively reduces n by a range represented as a power of 2, and the number of iterations corresponds to the number of binary digits in n, which is proportional to log 2, n. Since each iteration performs a constant amount of work, the overall time complexity remains O log n, providing a consistent and efficient solution across all cases. In this section, we'll explore some common mistakes that can occur when solving the IP to CIDR problem. One frequent error is the incorrect calculation of the subnet size. Each CIDR block, such as /24 or /26, corresponds to a specific range of IP addresses. Misunderstanding this mapping can cause you to either overshoot the intended range or leave out some IPs, leading to invalid solutions. Another common issue is failing to handle edge cases, particularly when IP addresses cross octet boundaries. For instance, transitioning from 192.168.255.255 to 192.169.0.0 can be tricky, as IPs wrap around octet values. Neglecting this can result in infinite loops or incorrect CIDR allocations. Lastly, an inefficient brute force approach that assigns /32 blocks individually can create significant overhead. This method, with its O(n) complexity, doesn't leverage the compact representation of CIDR blocks and is especially problematic for large IP ranges. Another mistake to watch out for involves how IP addresses are represented. Manipulating IPs as strings, such as splitting and joining octets, can be error-prone and inefficient. Converting them to integers allows you to use faster and more reliable bitwise operations for subnet calculations. Additionally, off-by-one errors can occur when determining the smallest CIDR mask for a range. For example, including one extra IP or missing one can result in an incorrect solution, which is particularly problematic when your output is validated against input constraints. These mistakes may seem small but can have a big impact on the correctness and efficiency of your solution. To perform well in interviews, it's important to fully understand the problem scope. Clarify whether the goal is strictly to minimize the number of CIDR blocks or if there are other considerations, such as performance or code readability. Leveraging bitwise operations is crucial, as converting IP addresses to integers allows for efficient calculations, such as determining the largest power of 2 or aligning IPs to subnet boundaries. Be prepared to explain the trade-offs of using a compact CIDR representation versus a brute force approach, especially for larger datasets. Recognize that this problem is fundamentally about efficiently combining ranges, which is a pattern that also appears in other problems like interval merging. Finally, communicate your thought process clearly during interviews by highlighting edge cases, such as range wrapping or ensuring minimal mask sizes, to demonstrate your attention to detail. This problem shares similarities with several others you may encounter. For example, LeetCode 751, the problem we're discussing, directly focuses on CIDR allocation. LeetCode 56, merge intervals, involves similar logic for merging ranges, while LeetCode 218, the skyline problem, deals with overlapping ranges and optimization. Additionally, LeetCode 338, counting bits, emphasizes binary representation and bitwise operations, which are key techniques for solving IP to CIDR. Beyond these related problems, there are alternative approaches to consider. The greedy approach involves always selecting the largest possible CIDR block for the given range. This method is efficient, with a time complexity of O log n, but requires careful handling of edge cases. Another option is a divide and conquer strategy, where the range is recursively divided into smaller CIDR blocks. While this method is conceptually simpler, it may use more space due to recursion. Another alternative approach is using pre-computed lookup tables for CIDR blocks that correspond to common IP ranges. This method allows for extremely fast lookups, as the work to calculate the CIDR blocks is done beforehand. However, it comes with limitations in flexibility, as it may not handle arbitrary ranges effectively. This trade-off makes it useful for situations where the IP ranges are predictable but less suitable for dynamic or unique inputs. Great job making it to the end. To recap, we tackled the IP to CIDR problem by breaking it down into manageable parts and exploring both naive and optimized solutions. Remember the importance of understanding bit manipulation and applying it effectively. Thank you for watching, and I hope to see you again in another problem walkthrough. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!